So today we're going to talk about intermolecular forces. And the first thing I want to go over with intermolecular forces are dipole moments or dipole-dipole interactions. And a dipole is the interaction between two atoms um, based on each atom's electronegativity. So electronegativity is the power of an atom in a molecule to attract all the electrons of that molecule and pull them towards itself. So what I mean by that is if you think of the planets, if we think of like planet Earth, like here's planet Earth, and Earth has its own gravitational force, right? So here's gravity, and the gravitational force wants to pull all things toward the planet. Right? So if you throw a ball up in the air, it's going to come right back down because of the gravitational pull of the Earth. Well, but then we have the moon out here, and the moon has less gravity than the Earth does. It has less of a gravitational pull. So it's going to it is going to have a gravitational force, but the gravitational force is a lot less. So if you go to the moon and you throw a ball up in the air, the ball might float away or it might just take a long time to get back down to the ground because the gravitational pull is a lot less on the moon than of the Earth. So what if we had the Earth and the moon next to each other and there was a ball, somebody threw a ball up into the air and the ball was right smack in the middle between the Earth and the Moon. Well, what would happen? Well, since the Earth's gravitational pull is stronger than the Moon's gravitational pull, the Earth's gravitational pull is going to pull the ball towards it, towards the Earth, and away from the Moon. So if we have, say we have all these balls in between the Earth and the Moon, well, what's going to happen to the balls? Are they going to just stay there or are they going to move? Well, they're going to be pulled by the Earth's gravitational force because the Earth's gravitational force is stronger than the moon's, and the balls are going to fall back down to Earth. They're not going to fall over to the moon because the moon has less of a gravitational force. Now, how do we know which element in a bond is going to pull the electrons toward it and not the other element, not the other atom? For instance, um, if we have carbon monoxide, so we have an atom of carbon and we have an atom of oxygen, and we have these electrons between them. Well, where are these electrons? These electrons are not going to just stay put in between the carbon and the oxygen. The electrons are constantly orbiting around the molecule, just like a planet orbits around the sun, and they're going to be constantly in a constant state of movement. So if we look up at our periodic table, we can find out which of the carbon or the oxygen has more electronegativity. And that is going to be the one that pulls the electrons toward it. In this case, oxygen has more electronegativity, so it's going to pull these electrons towards the oxygen, and the electrons are going to end up being over here towards the oxygen. They're just going to move slightly, and when they do their orbit, they're going to kind of lean over toward the oxygen side of this molecule instead of the carbon side of this molecule. Now, how do we know that? How do we know which is more electronegative than the other, carbon or oxygen? Well, if you look at the periodic table, and we have the periodic table right here, the periodic table, as I've said before, the periodic table gives you a lot of clues for everything you need to know about chemistry if you know how to read it right. So if you look at where all the elements are placed on the periodic table, up here in the upper right hand corner, the fluorine, and we just disregard the noble gases because the noble gases don't really interact with other elements, so we just don't worry about them. So we go over to the next column where fluorine is at the top of that column, and fluorine is the most electronegative. And there are periodic tables that give you, instead of the numbers, the atomic number and the atomic mass. Instead, they have numbers on there telling you exactly what the electronegative measurements are. But the trend is you don't need to have one of those special periodic tables to know that the trend is the most electronegative is the fluorine up in the upper right. And as you go down and to the left, you get to the least electronegative, which is francium. And so if you know this, if you know that the most electronegative is up and to the right and the least electronegative is down and to the left, then you can, by comparison, you can tell which atom is going to be stronger, have a stronger electronegative pull that's going to pull the electrons towards it in the molecule. So you can look at it like a tug of war between the atoms for the electrons. The electrons are getting tugged back and forth between the atoms, and whichever atom has the strongest electronegativity is going to win, is going to pull the electrons towards its side of the molecule. So for instance, let's take a look at oxygen and hydrogen, the oxygen and hydrogen bond. So here's oxygen and hydrogen, and they share these two electrons in the form of a single bond. So there's an electron here and an electron here that are between the oxygen and the hydrogen. Well, first you go to step number 1, and you look and see that oxygen is more electronegative than hydrogen. So oxygen has more of like a gravitational pull or a magnetic pull towards it. So therefore, it's going to pull the electrons, pulls the electrons in that bond toward the oxygen atom and away from the hydrogen atom. So as you can see down here, I have little arrows showing the electrons are going to be moving toward the oxygen and away from the hydrogen. Now, when you're writing things down in chemistry, this is how you're actually going to write this dipole. This is called a dipole moment when the oxygen's pulling the electrons away from the hydrogen. And you're going to write it down like this. The arrow is going to be pointing toward where the electrons are going, which is to the oxygen side. And then on the hydrogen side, you're going to have this little cross over the end of the arrow, which looks like kind of like a plus sign. And that's because when all the electrons go over toward the oxygen, it's going to make the oxygen a little bit more negative because electrons are negative, and therefore if all the electrons go crowding around the oxygen, then all that negativity that the electrons have are going to rub off on the oxygen. The oxygen is going to be a little bit more negative. And the hydrogen, since all the electrons are leaving the hydrogen and electrons are negative, that's going to leave the hydrogen with a slightly positive charge because it's lost its electrons. So if you look at number 3 here, we call this a partial negative charge and a partial positive charge because these are different. This is different than the charges of ions. You know, like sodium has a +1 charge on it, a sodium ion, and a chlorine atom has a -1 charge. This is a different ball game. This is a different kind of charge. The molecule itself is still balanced. It just makes the molecule kind of heavy on one side with electrons. So we have oxygen and hydrogen, but if all the electrons have moved over here on the oxygen side, it's going to be bigger than the hydrogen side. The hydrogen's not going to have any electrons around it. So we're going to call this side partial negative. The oxygen side is going to be partially negative, and partial is just denoted by the lowercase delta sign, which is like a fancy little lowercase d, and then we put a negative sign after it. And then hydrogen is going to be partially positive because it doesn't have any electrons around it. So again, that lowercase delta, which is like a little fancy d, with a positive sign after it. So this is how it can be drawn down here in number 4. We have the arrow here. The arrow is pointing toward where the electrons are being pulled, and where the electrons are leaving, we have a little cross at the end of the arrow mark, and I think it looks like a plus sign because that goes along with the fact that the hydrogen end is partially positive. And then, of course, the oxygen end is going to be partially negative because that's where all the electrons are hanging out. So, who cares, right? How does this apply to anything? Well, let's take a look at the water molecule. And the water molecule is, as you know, it's O with an H on either side of it, and it's a bent molecule. So it looks like this. So an O and 2 H's, and then the O has extra electrons up here. And we know that the oxygen has a stronger electromagnetic force than hydrogen does. So that means oxygen is going to be pulling all of the electrons in the bond toward the oxygen, toward itself. So all the electrons are going to start migrating up toward the oxygen and away from the hydrogen. So each hydrogen that's attached to the oxygen has its own dipole moment. It has this little, see this little arrow pointing toward the oxygen? That's pointing toward where the electrons are going to go. And then there's this little plus sign on the end of the arrow by the hydrogen, meaning that the hydrogen is going to be partially positive. And the same goes on the other side here. The hydrogen is going to be partially positive, and the oxygen is going to be partially negative because all the electrons are drifting up toward the oxygen, and electrons are negative. So therefore, if you look at a water molecule, and I just drew it in a different way down here, but still the same thing, these are the H's, and this big one is the O, the oxygen. Those electrons that are orbiting around the hydrogens are going to break off and start moving up toward the oxygen. Because, see, the electrons, once a bond forms in a compound or a molecule, the electrons don't only revolve around that one atom anymore. Now they're revolving around the entire molecule as a whole. So the electrons are going to move up toward the oxygen in this molecule, in this water molecule, leaving the oxygen end of the molecule partially negative and the hydrogen end of the molecule partially positive. So what happens now? Well, when two water molecules get together, and so here's the H's, and here's the big O, here's H, and here's the big O. When two water molecules come together, this partially negative charge on the oxygen end of the molecule, opposites attract, so it attracts the partially positive end of another water molecule, so the hydrogen end of the water molecule. And so water molecules actually stack on top of each other from oxygen to hydrogen of the next molecule, because the oxygen and the hydrogen of another molecule, another water molecule, are attracted to each other. Okay, now let's look at a larger molecule of several atoms put together. Let's look at chloroform, which is CHCl3. So in CHCl3, C carbon, carbon's in the middle, and then the H is coming out of the, well, let's say the top, it doesn't really matter, but H is coming out of one end of it. And then the other three are Cl's, or chlorines, and so the Cl's are coming out. There's a Cl coming out of the front bottom, There's a Cl coming out of the side, and then this little hash mark thing means this is going back in the back. Since you can't draw in 3D, this Cl is going in the back. So it looks kind of like a tripod, and then the H is on top there. So this CHCl3 chloroform, if you want to know dipole interactions of this big molecule, you have to look at the individual dipole moments between each individual. So first we have the H and the C, the hydrogen and the carbon. And if you look at the hydrogen and the carbon bond, carbon has a greater electronegativity than hydrogen. So the hydrogen electrons, the electrons between the hydrogen and carbon, are going to be pulled toward the carbon atom. So that's why we have the arrow going toward the carbon. So let's draw this up here. The arrow is going toward the carbon atom, and that means the little plus sign is back here toward the hydrogen. So that makes hydrogen partially positive and carbon partially negative. And then you have the bonds between the carbon and the chlorine. So the carbon and the chlorine is more electronegative than the carbon. So all of the electrons that the carbon has, and then all of the electrons that that have migrated toward the carbon, now are migrating toward the chlorine, because the chlorine is more electromagnetic than carbon. So let's write this up here. From carbon to chlorine, the arrow points toward chlorine, and the carbon gets the little plus sign at the end of the arrow. The carbon goes toward chlorine, and the carbon gets the plus side, and the carbon electrons migrate towards the chlorine. They're magnetically pulled towards the chlorine. So if you can see this pattern, the electrons are going down this way, and then they go out this way. So all the electrons are migrating in one direction. They're all migrating down toward the chlorine. So that means all the electrons are going to be down toward the chlorine end of this molecule, and there aren't going to be any electrons over on the hydrogen end of this molecule. So since all the arrows point downward and all the arrows are pointing toward chlorine, so all of the electrons are migrating toward the chlorine end of the atom, that makes one end, this hydrogen end of the atom, partially positive, and the chlorine end of the atom partially negative, because it has all the electrons down here toward the chlorine. So in the case when a molecule has all the electrons shifting towards one end of the molecule and away from the other end of the molecule, then the one end of the molecule is positive and the other end of the molecule is negative, and that is what a polar molecule is. That would be polar, and this would be the sum of the dipole interactions between the individual bonds of the hydrogen, the carbon, and the chlorine. So this would be a polar molecule in this case. So let's take a look at another molecule. This time it's Ch4 methane. And so Ch4, so that means there's one C and there's four H's. So C is the central atom in this molecule, and then the four H's come off on either side of it. So we have an H coming out of the top, we have an H coming out of the side here, we have an H coming up out of the front, and then this little hash mark thing means this H is going backward. Since we can't draw in 3 dimensions, this is the best I can do, so that H is pointing back. So in order to find out what is going on if there's a dipole force in this molecule, we need to look at the individual dipole moments between each bond, between the C and each H bond. So C is more electronegative than H. So that means C is going to be taking all the electrons. All the electrons are going to be migrating from the H to the C. So the electrons all move toward the C. So let's see what this looks like up on this molecule we drew. From the top H, the H on top, the electrons are going to be moving down to the C, to the central atom in the molecule, and the H gets that little cross, the little plus thing there. And then this H back here, the electrons are going to be moving up to the central C from the H. And then this H in the front, the electrons are going to be moving up toward the C and away from the H. And then this H on the side, the electrons are going to be moving up toward the C, away from the H. So now this is a different example than the chloroform we looked at, because in the chloroform we looked at, all the electrons were moving downward. They were moving down because we had the H up here, and then the C in the middle, and then the chlorines were down here. And all the electrons are moving in the same direction, downward, making all the electrons down here by the chlorine, and none of the electrons up here by the hydrogen. But in this one, in methane, all of the electrons are moving toward the center carbon. Do you notice that? So here's the carbons in the middle, and all the electrons are being pulled toward the carbon because the carbon is the most electronegative atom in this molecule. And so since all of these electrons are being pulled toward the center, they end up canceling each other out. So this is going to be a nonpolar molecule because there isn't one end of the molecule with a lot of electrons and one end of the molecule with no electrons. All of the edges, all of the ends or the edges of the molecule have the same amount. They're all partially positive. All of these are partially positive. And then that makes the carbon in the center partially negative. So the ends of the molecule aren't lopsided. The polar, if it's polar, then the edges of the molecule, the ends of the molecule are going to be lopsided. One side of the molecule is going to have more electrons than the other side of the molecule. But in this case, all of the electrons are going toward the center, toward the carbon. And so they're not lopsided. All of the ends of the molecules are the same. So this is going to be nonpolar and therefore not have a dipole interaction.